Last time we have seen the method of a reduction of order. For that purpose, we consider the second order linear differential equation y double dash plus px into y dash plus q of x into y is equal to rx. And this method of reduction of order is also applicable for the differential equation having the variable coefficient. The Up to this, we have seen only those methods which are applicable to the differential equations having the constant coefficient. Now we want to see the method of reduction of order and the method of variation of parameters. These two methods are applicable those for those differential equations having variable coefficient also, or it is also applicable for the constant coefficient. Now here we have considered this, suppose y is equal to y1 of x is a solution of the associated homogeneous differential equation y double dash plus p of x into y dash plus q of x is equal to 0. Then this y1 satisfy this differential equation, associated homogeneous differential equation, and we take the substitution y is equal to y1b. With this substitution, we convert the dependent variable y to the dependent variable b, and then from this we find y dash, y double dash, and we substitute these values in the given differential equation, and then rearranging this differential equation, we obtain this differential equation. Now here, after this, we have to take again the substitution. W is equal to V dash. Therefore, W dash is equal to V double dash. Therefore, with this substitution, second substitution, we reduce the order of this differential equation from second order differential equation to the first order differential equation. Now this is the first order, first degree differential equation, and we know that how to obtain its solution. If we solve the differential equation, then we obtain the relation between W and X. Then in this relation, we substitute W is equal to V dash, means this is dV by dx. Then this relation is converted into first order, first degree differential equation. Again, solving this first order, first degree differential equation, we obtain a relation between V and X. And in this relation, we substitute V by Y upon Y1. Then we obtain the general solution of the given differential equation by the method of reduction of order. We have seen this in the last lecture. Now we will see the examples based on this. Solve the equation d square plus 2d plus 1 of y is equal to e to the power x minus 1 to the power minus 2 by the method of a reduction of order. Now here we have seen that how to solve. First we must know one solution of the associated homogeneous differential equation. This is a differential equation with constant coefficient. Therefore, we have seen previously how to obtain the solution of the homogeneous differential equation with constant coefficient. Using that technique, we find the one solution y is equal to y1 of x. If there is the variable coefficient, In that case, they give us one solution. Now here for the differential equation, we know that if we consider the auxiliary equation, then the auxiliary equation is m square plus 2m plus 1 is equal to 0. This is m plus 1 bracket square is equal to 0. Therefore, roots of the auxiliary equations are -1 -1. Roots are real and repeated. Therefore, two linearly independent solutions are e to the power minus x and x e to the power minus x. Out of these two linearly independent solutions, we choose any one solution as to be y1 of x. For our simplicity, here we choose y1 of x is equal to e to the power minus x. Then we substitute y is equal to y1b. This is equal to e to the power minus x into v. This is our equation 2. From this find y dash and y double dash. After obtaining the values of y dash and y double dash, then from this equation 2, equation 3 and from equation 4, we substitute these values in this equation. After substituting these values in this equation, we change the dependent variable y to the dependent variable b. After substituting, we get this differential equation. Now, rearranging this differential equation, collect the coefficient of v double dash, b dash, and v. We get this differential equation in this form e to the power minus x y v double dash is equal to e to the power x minus 1 whole to the power minus 2. We obtain this after simplification. We obtain these things. Now here in this equation we take the substitution w is equal to v dash. Therefore, w dash is equal to v double dash. Then with this substitution, this equation becomes e to the power minus x into w dash is equal to e to the power x minus 1 whole to the power minus 2. Then take this e to the power minus x to the right hand side and rearranging the equations, we obtain dw by dx is equal to e to the power x divided by e to the power x minus 1 whole square. Now this is the first order first degree differential equation. Now to solve this, here very simple, we convert first this into the variable separable form, taking dx to the right hand side and then integrating, we obtain this w is equal to integration of e to the power x upon e to the power x minus 1 whole square into dx plus c1. Now we evaluate this integral. To evaluate this integral, for that purpose, we use the method of the substitutions. We take the substitution, put t is equal to e to the power x minus 1. Therefore, e to the power x is equal to t plus 1. And then taking the derivatives and so on remaining part, you are able to solve this. After evaluating this integral, we get this integral is minus 1 upon e to the power x minus 1 plus c1. Now here again substitute the value of w as to be v dash, means it is dv by dx. Then again this is the first order first degree differential equation in v and x. Now again take dx to the right hand side, then this becomes in the variable separable form and integrating this, we get v is equal to integration of minus 1 upon e to the power x minus 1 plus c1 into dx plus c2. If separate this, we get this is integration of c1 dx is c1 into x plus c2. We want to evaluate this integral. Integration of 1 upon e to the power x minus 1 dx. For this purpose, we take the substitution, put t is equal to e to the power x, or you may take t is equal to e to the power x minus 1. You decide yourself. I have taken t is equal to e to the power x. Then dt by dx is equal to e to the power x, or dt is equal to e to the power x dx, but e to the power x is t. Therefore, from this we obtain dx is equal to dt upon t, and substituting this in the 2, we get integration of 1 upon e to the power x minus 1 dx is equal to integration of 1 upon t minus 1 into value of dx is to be dt upon t. Now, by partial fraction, we rearrange this. This is 1 upon t minus 1 minus 1 upon t dt. We know that how to rearrange this. If we simplify this, we get this. Now, separating this, the integration of this log of, you may take absolute value of t minus 1 or log of t minus 1 minus log t. Sometimes some books they use the absolute notation for this log of absolute value of t minus 1 minus log of absolute value of t, or you may write this as it is. Now here use the substitute the value of t, then use the rule of logarithm and all that things. Rearranging this, we obtain this and we substitute this value of the integral in this equation 1. Therefore, we get v is equal to minus log of e to the power x minus 1 plus log of e to the power x plus c1x plus c2. Now rearranging this log of e to the power x is x log e, and log e is 1. We obtain this. Now collect these two terms together, we obtain this. Again here, we substitute the value of v as to be what? Y upon y1. Substituting this value of v, we get this relation, and this is the general solution of the given non-homogeneous linear differential equation by the method of reduction of order. I hope you understand. We see few more examples. Now take the next example. Use the method of reduction of order to solve d square minus 5d plus 6 of y is equal to 2 e to the power x. Again, we must know one solution of the associated homogeneous differential equation. Here, the auxiliary equation is m square minus 5m plus 6 is equal to 0. Therefore, the roots of the auxiliary equations are 2 and 3. Therefore, the linearly independent solutions are e to the power 2x or e to the power 3x. Now, I have chosen here y1 is equal to e to the power 2x. Now, with this substitution, we take put y is equal to y1b, means this is equal to e to the power 2x into b. Then from this find y dash. We obtain here from this using the product formula y dash, again y double dash, and substituting these values from equation 3, 4 and 5 into this equation 1, we change the dependent variable y to the dependent variable v with this substitution. Rearranging this differential equation, we obtain the final differential equation is to be v double dash minus v dash is equal to 2 e to the power minus x. Now remember that v with this substitution y is equal to y1b, we substitute these values y dash, y double dash, sorry, the value of the y double dash, y dash, and y in the given equation in terms of v, we obtain this equation, and in this equation, remember always the coefficient of v comes to be 0. Coefficient of v comes to be 0. There is no term of v, remember, in this equation. Now in this equation, again we take the substitution w is equal to v dash, therefore w dash is equal to v dash, and with this substitution we convert this differential equation into the first order first degree differential equation. Here d2v means v double dash is w dash means dw by dx minus dv is w is equal to 2e to the power minus x. This is the linear differential equation of first order. We know that how to obtain this solution. If you compare the differential equation as our standard linear differential equation, dy by dx plus p of x y is equal to q of x, then its solution is y e to the power integration of p of x dx is equal to integration of e to the power integration of p of x dx into q of x dx plus c1. We have seen this in a 5 basic class. Using that formula, here p of x is minus 1 and q of x is 2e to the power minus x, and the dependent variable is w. Therefore, its solution is w e to the power integration of minus 1 dx is equal to integration of 2e to the power minus x, and integration of this is minus x dx plus c1. Simplify this, we get this. Again, evaluate this integral on the right hand side, we obtain this. And now take e to the power minus x to the right hand side, we obtain w is equal to this. Again, in this equation, we write w is equal to dv by dx. And again, we obtain the first order, first degree differential equation in v and x. Now take this x dx to the right hand side, then this is in variable separable form. Integrating, we obtain this. Simple integration is there. Therefore, we obtain v is equal to e to the power minus x plus c1 e to the power x plus c2. And again here, we substitute y, v is equal to y upon y1. Our y1 is e to the power 2x. Therefore, we substitute y v is equal to y upon e to the power 2x. We get this, and then rearranging this equation, we obtain the final general solution as to be y is equal to e to the power x plus c1 e to the power 3x plus c2 e to the power 2x. This is the required general solution of the non-homogeneous linear differential equation by the method of reduction of order. I hope you understand this method properly. We have seen the two examples of this type. In the next lecture, we see the examples of the type in which the differential equation having the variable coefficient, then how to obtain its general solution by the method of reduction of order. Today we stop this our lecture.